What's up everyone, welcome back to my channel. Today we're going to look at an easy but quite interesting number theory problem that I actually found from the textbook that I used when I was in undergrad taking the number theory course. So there are actually 3 parts in total. We're going to look at all 3 parts today and see how to actually understand the problem with the number theory behind it. So given that p is a prime number, now again I'm clarifying that it is a prime number, so don't try to argue that well it's 4 prime or whatever. So we're just using the basic definition of what a prime number is, not in thinking as a ring or whatever. It's just basic prime numbers that we can think of when we have the natural numbers. Okay, so first part of the problem says try to find, well, it says find the value of the sum from 1 to p minus 1. And of course we already know the formula, but this time we're going to try to find the value in mod p. In other words, we're trying to divide the whole thing by p and want to see what the remainder would be. Well, of course, it would be very easy in this situation. If we try to add the natural numbers up to p minus 1 term, so we will use the formula which says the sum of the natural numbers from 1 to, let's say we don't have a variable here, let's call k. We'll actually get, if we have something such as from 1 to k, we'll actually get k times k plus 1 over 2. So for the first part of the whole problem, we can actually get this answer quickly by using the formula to see that this summation here will give us k, which is p minus 1, the last term that we have, times 1 plus that, which is of course p, all divided by 2. But again, we're not done yet because we need to divide by p and want to see what the remainder is. So what are we going to do? Well, of course we might think that if we divide by p, we'll actually get no remainder, right? Here is the problem. When we say p as a prime number, we need to consider that p could be even, where of course that will mean that p is equal to 2, and that's the only case. And when p is odd, why does it matter? Here is the reason. Suppose that p is odd, meaning that p is 3 or bigger. In this case, of course, p as a prime number cannot be divided by 2, and we know that from the original formula. This fraction here is in fact an integer or natural number, meaning that if p cannot be divided by 2, p minus 1 over 2 itself must be an integer, so that multiplied with the prime p, we will still be able to get the integer back. Or in other words, p minus 1 is a multiple of 2. So if p is odd, we in fact would get that p minus 1 all over 2, this part here, is going to give us an integer. Let's call it L. Then we actually get L times p, which of course is an integer that is divisible by p, and meaning that we will actually get 0 as the remainder. Now, on the other hand, if p is equal to 2, what's going to happen? Think of the summation. The meaning of it is we're going to start from 1 and add all the terms up to p minus 1. But what's p minus 1 in this case? We actually get p is equal to 2, meaning that p minus 1 is 1. Therefore, the consecutive sum here is actually starting from 1 and ending with 1. In other words, there's only one term here. So for that situation, when p is equal to 2, we actually get a different result, that this summation is in fact just equal to the only term, 1. And of course, if we try to divide by 2, the remainder is still 1. Where if p is a odd prime, meaning that if p is greater than or equal to 3, this summation is going to be divisible by p and is going to give us 0 as a remainder. Pretty interesting, huh? We now need to think that when we try to solve or try to find a value, we might need to break it into cases so that we will be able to cover everything and we're not going to fall into the trap. Why does this matter? Here comes the second part of the problem. Part B. So part B is to try to find the value of the sum of not the natural numbers up to p minus 1 anymore, but we're going to add the first p minus 1 square terms. So we now raise it to the second power. How is it going to affect us? Well, again, we can use the formula to show that this sum will give us p times p plus 1 times 2p plus 1 all over 6. Then what are we supposed to do? Well, now we need to pay attention to the denominator. We have a denominator 6 here, which in fact can be rewritten as 2 times 3. And that is going to give us something different, which is actually similar to part A, that we need to separate out the p equals 2 from the rest. Here we need to break it into 3 cases. When p is equal to 2, when p is equal to 3, and when p is strictly greater than 3, which is again will be greater than or equal to 5. So of course, when p is greater than or equal to 5, then we know that this part will be an integer, as we know from the formula, where p itself is a prime number that is not equal to 2 and not equal to 3. It means that the 2 and the 3 in the denominator will be cancelled out with p plus 1 term and 2p plus 1 term respectively, the two factors. Therefore, we can assume that this big part here will be an integer, L again, times the prime number that we have, p. And therefore, when p is greater than or equal to 5, we actually get the results that p, this sum here is going to be congruent to 0 mod p. Now, if we try to think of the other 2 cases, it's not going to work anymore. But since there are, for each case there's exactly one value, we can actually kind of brute force it. So for example, when p is equal to 2, we see that this sum is actually starting from the first square term, which is 1 square or 1 plus, what is it? There's no more, because if p is equal to 2, the last term that we have will be 2 minus 1, which is 1, or in other words, it will just be, the last term will just be the first term. Therefore, when p is equal to 2, we actually have the sum is just equal to 1 itself, of course, which is congruent to 1 mod p. Now, if we consider p equals 3, what our last term will become, it will be 3 minus 1, which is 2, meaning that the second term will already be our last term. And therefore, our last term will be just 2 square. And what do we get? We'll just have 1 square plus 2 square, which is of course equal to 1 plus 4 equals 5. So in this case, when p equals 3, we actually get that the total sum is congruent to 5, which is again, if we try to take it in mod p, it will be congruent to 2. Again, that means that we're going to divide by 3 and find the remainder again. And that is divide by 3, we have 1, remainder 2. Then what are we going to get? Well, let's see. Since if we're trying to continue this problem here, we're going to get excuse me. For here, we actually will get minus and minus, but it is not going to affect the results. Again, that's because the original setup is if we add the first k terms for square, we will be able to get 1/6 times k plus 1 times 2k plus 1. But after we substitute it, the k plus 1 term will turn into p here, and here we actually get p minus 1 instead, and we have 2 times k, which is p minus 1, so we get 2p minus 2 and then plus 1. But again, we still have the p term to help us canceling out. It's not going to change the overall result. All right, then what we're gonna do next? For the last part of the problem, we are going to change the 2 into some k power. Now, of course, we actually saw from the last two parts of the problems that we need to separate into cases. But suppose that we have the k here is actually getting controlled by again, it will actually control the denominator later on in the whole expression. We can actually see that for the first finitely many prime numbers, they might actually end up with different results. Just like when k is equal to 1, we have the first prime number is not going to be equal to 0. And then when we have k is equal to 2, the first two first two prime will not give us 0 after we divide by p, okay? But for the rest, we actually get that this sum here is congruent to 0 mod p for large enough p. So our assumption here is that this here is going to be congruent to 0 mod p for any large positive integer k here. All right. How are we supposed to do that? Well, now we need to think back to the formulas. So when we consider the sum of the first n terms, again, I shouldn't use n here, but let's say we use k here. Then we actually get the formula 1/2 times n times n plus 1, where here we have p minus 1 to replace the last term. So we can just stick with n again, so that we actually see that if we add the first p minus 1 terms of the natural numbers, we get 1/2 times p minus 1 times p. And again, we if p is large enough, then it will be a prime number that is not divisible by the not divisible by the denominator. In other words, it is of course a prime number that is not a multiple of the denominator here, no matter how we break it up. Because again, here we can assume that p is strictly greater than 2. Then we will see that in order to be an integer, it has to be the p minus 1 term in to cancel with the 2 to keep it as an integer. Okay, so with the similar argument, we can actually say that again. For the square, we get the following: 1/6 times p minus 1 times p times 2p minus 1 here, where if we choose a p large enough, so in this case, if we can choose p to be strictly greater than 2 and 3, of course, where 3 is the largest prime factor of the denominator here, then we will be able to force the p to be separated out, and then the rest will be able to simplify into an integer and then times the p showing that after we try to take it in mod p, this whole thing will still be an integer, or it will actually turn into 0. It has no remainder here. So if we now try to check one more as an example, let's say n to the third power. If we try to add sum up the first p minus 1 terms of the cube, the perfect cube, we get, of course, if you don't memorize it, it's okay. If you memorize the formula, you actually get 1/4 times p minus 1 quantity square times p square here. And again, in this case, the denominator is 4, so the largest prime factor of it is 2. As long as we choose p to be strictly greater than that prime factor, we will be able to see that since p is a prime number, it cannot be divisible by 4 or any of the prime factor here in the denominator, meaning that all those the whole denominator has to cancel out with the rest of the expression. It will cancel out with the other factors, and then leave the whole thing as an integer times the p here, or p square, meaning that now it is actually a multiple of p. Again, that will be able to show us that p as a prime number, if we divide it, we will get 0 remainder. Then if we continue the following, we will be able to see that when we try to consider the expression of the sum of the first p minus 1 terms of whatever integer power, positive integer powers we have, the closed form of it, meaning that the right hand side here is some fraction times something times some p here. There will be at least one copy of p that's going to multiply with the rest. And therefore, again, if we can choose the p large enough, in the sense that p as a prime number is larger than the largest prime factor in the denominator. And again, if we try to continue, for example, to the 4th power, it will be 1/30 times p minus 1, and then times p, and then times something. Now, then we'll be able to see that this whole expression on the right will still be a multiple of p, and we will get that this expression will be congruent to 0, or this value is equal to 0 if we're trying to take it in mod p. Now you may ask, when we try to look at the expression of the actual formula out, okay, such as if we try to take from the first n terms, don't we have we actually get 1/2 times k times not k here, it will be n here, n times n plus 1. Then but then if we replace the n, we will actually get p minus 1, meaning that we're not really looking, we cannot look at the n term. We know that the n term will be there, but how about the n plus 1 term? Because again, now we turn the n into p minus 1, and then the n plus 1 term will turn into the actual p that we're trying to look for. Do we actually guarantee the n plus 1 there? Yes. How do we know? I actually had a video back then that is trying to show the method of generating the summation from the first n terms of the power numbers, such as the first n natural numbers, the first n perfect squares, so on and so forth, including the 4th power. And then I also show the method of how we can generate the summation from the previous power. So if you see that video, if you try to watch that video again, you will see how we can actually guarantee that not only the n term will show up on the right hand side for all the summations, but the n plus 1 term will also pop up for all the terms or all the sums. Therefore, we can guarantee that no matter what positive integer powers we're taking, we will be able to get a factor, the factor of p prime number here, so that we'll be able to divide by p and and end up with zero remainder. Okay, that's it. I hope you all enjoyed this video. Don't forget to like and subscribe to my channel so that you can find more of my other videos, and turn on the notifications so that you won't miss any of my new videos either. I'll see you guys next time.